Hello, I'm Adam Wu. In the previous episode, we discussed whether the tolerance of a datum itself can be larger than other tolerances. For example, here the flatlist is larger than the profile tolerance. Is this considered an incorrect specification? In the previous episode, we explained that since the datum plane is established by external tangency, its position and orientation relative to the part are unique. Therefore, no matter how poor the flatlist of the datum feature is, the profile tolerance zone here still has a unique position and orientation relative to the part. So, our conclusion in the previous video was that, from a logic standpoint, having a flatlist of 0.2 here and a profile tolerance of 0.1 here is not an incorrect specification. Based on the conclusion from our previous video, the flatlist of the datum feature is not directly related to the profile tolerance here. So, can we say that the flatlist of the datum feature is not important? Keep in mind, we cannot analyze this only from a theoretical perspective. We also need to consider real-world inspection, manufacturing, and assembly. If the datum feature has a poor flatlist, could it introduce other negative effects? This is our designed 3D CAD model, and this yellow one represents the actual part. The lower surface of the yellow actual parts is the datum feature. It is intended to be a planar feature, but in the real microscopic world, due to the manufacturing imperfections, it has been machined into a long ideal surface with form deviation, effectively becoming a curved surface. Now, I'm positioning it correctly to examine how poor flatlist of the datum feature affects inspection, machining, and assembly. Let's first look at the impact on measurement. If we are using a CMM for inspection, due to the inherent randomness of measurement sampling, suppose that in the first measurement, the system randomly collects these points. Based on the external least squares method, the fitting datum plane is established here. Then we perform a second measurement, again randomly sampling these points. The resulting fitted datum plane would now be located here. Have you noticed that in the first measurement, the fitted datum plane was located here, while in the second measurement, the fitted datum plane shifted to here? For the same part, the resulting datum definition is inconsistent, meaning the reference system itself changes between inspections. As a consequence, the measured value of the profile tolerance of the upper surface will also vary from one measurement to another. In a production environment, this leads to a key issue. When the datum surface itself has poor flatlist, the repeatability of measurement is poor. Now, let's look at the negative impact on machining. This is the actual part, and the machined lower surface is shown here, which is not ideal. In current process, we use the lower surface as the datum to machine the upper surface. As you can already notice, the lower surface of the part is convex in the middle, which means that during fixturing, the contact condition between the actual parts and the fixture table is unstable. They may be clamped in a relative position like this. After a single pass of the milling cutter, the upper surface is then machined Finally, the upper surface is machined into this shape. If a second part is clamped, due to the unstable contact condition between the part and the fixer table, it may be constrained in a different orientation or attitude during fixturing. For example, it may be clamped in this orientation, and then the milling cutter performs a single pass. Then the part is machined into this shape. Have you noticed that because the datum surface, the contact plane with the fixture table has poor flatness, the fixturing condition is not unique or repeatable. As a result, the machined part may end up in one configuration, or it may end up in another configuration. Therefore, our conclusion is that when the datum plane itself has poor flatness, it can lead to poor machining stability and process robustness. Now, let's look at the negative impact of poor datum flatness on assembly. This is the actual part. Notice there is a hole whose position is critical. The lower surface of this part has, for some reason, been machined into a convex shape in the center. This is the mating component in the assembly. After two parts are assembled, they are fastened with screws. Now, we assume that the mating part has very high stiffness, while the yellow part has relatively low stiffness. When the screws are fully tightened, due to the clamping force, the assembly may force the two mounting surfaces into a conforming contact condition, effectively pull them flat. Clearly, this will introduce assembly-induced elastic deformation, where the part is constrained and deformed under preload, rather than sitting in its natural stress-free state. Finally, the two parts are assembled in this condition. Have you noticed that in the microscopic world, the yellow part has already undergone elastic deformation? As a result, the position of the hole will also shift. Therefore, our conclusion is that since datum A is typically the mounting surface, poor flatness of the mounting surface can cause the part to undergo elastic deformation during assembly. As a result, this deformation will compromise the accuracy of the other functional features and may introduce potential functional failure of the product. Alright, let's briefly summarize this video. Although, in theory, if the tolerance of the datum itself is larger than that of other features, its definition is still clear and it will not affect the evaluation or acceptance of the part. In practice, we must also consider its impact on measurement, machining, and assembly. Therefore, the tolerance of the datum feature itself is actually extremely important. If the datum surface has poor flatness, as shown in this case, it will reduce the repeatability of measurement. It will degrade machining stability. In assembly, it will affect the accuracy of other functional features and ultimately reduce product robustness. That's all for this video. Hope it gives you some useful insights. I'm Datum. Follow me. Let's keep improving together.